This final section is going to be on fertilization and the response of trees to fertilizer. So we're talking about mineral elements, and it should be obvious that one way to manage the nutrition or nutrient availability of forest is to add fertilizer. And fertilization is a practice that's frequently done especially in intensively managed forests. And that's because forests that we're managing are often growing on nutrient poor sites. Especially conifers tend to be adapted to nutrient poor sites, so they're often growing on nutrient poor sites. But in addition, most of the nutrient rich sites in settled parts of the world were long ago cleared of forest and planted to agriculture. So the more rich soils, we're growing food on those sites. So generally when we're managing forests, they're on more nutrient poor soils. So in order to manage that, to increase growth rate on those soils, we often add fertilizer. So here's an example in Scots pine, which is a really important European species. And this shows a cookie from a Scots pine. This pine's probably, 35, 40 years old. And it shows in the center, and there's a zoom here, in the center, in the early stages of this tree's life, it was growing really, really slowly. See those really narrow rings? But at this point, at this year, they added fertilizer. And then boom, here's one growth ring, here's another growth ring, here's another growth ring. Those growth rings after fertilizer are maybe 10 times larger than those tiny little growth rings before fertilizer. That, is a classic demonstration of nutrient limitation. If you have a tree and you add fertilizer, whether it's one element or multiple elements, and growth increases after the addition of that fertilizer, and in a control there's no change, then that tells you that site is nutrient limited for whatever elements you put on there. So clearly this was a nutrient limited site, and the addition of fertilizer increased rates of growth on that site. So fertilizer is a commonly used approach for managing nutrition, especially in pine forests. Now in some parts of the world, there's been observations of productivity declines as multiple rotations of trees are grown on a site. If you think back to that table I showed you where I circled, the amount of nitrogen contained in stem, bark, for instance, and branches, and those nutrients are carried off at harvest. Well, in some places, like I said, especially in Australia, it's suspected that sort of multiple rotation cropping of the site, especially in the absence of additional fertilizer, actually results in declines in productivity with subsequent rotations. So for instance, this rotation, the trees might actually grow more slowly than they did the previous rotation because we've induced nutrient deficiency by carrying nutrients off the site. What I will say is that is actually pretty rare. In the United States, and especially in the southeastern United States, we don't observe that. One, because fertilization is a fairly widespread practice. We seldom run into declines in productivity with additional rotations. And in fact, what we've found is exactly the opposite. Each subsequent rotation that we've harvested, productivity has been quite a bit higher than productivity in previous rotations. One, because the genetics we're using are better. Two, because our silviculture is better. So we're actually seeing the opposite. We're seeing enhanced productivity with each generation or each rotation of trees that we're growing on sites in the southeastern U.S. So we do need to be aware of the phenomenon of productivity declines that might be associated with removal of nutrients from the site. But that can generally be managed through fertilization, and we just need to pay attention to it. Here's another example of a nutrient story. These are cross-sections from 4-year-old loblolly pine trees. So this bottom loblolly pine tree here, This is 4 years old, but it was just growing. This is a 4-year-old loblolly pine tree that received fertilizer, but also control of competing vegetation using herbicide. So you can see the addition of fertilizer and the removal of competitors greatly increased the growth rate of this tree. You know, that tree in terms of biomass is many times larger than this tree. These cookies, these cross sections were from that example I showed you at the beginning of this lecture. Right here. This big tree, this is on a fertilizer plus herbicide plot. So this plot has had a lot of fertilizer added to it, and all the competing vegetation, which is competing for nutrients as well, has been removed. Whereas this tree is growing in an adjacent plot, same age, but it has had no fertilizer added, and it's competing with all these palmetto and gallberry for nutrients, and it's much smaller. So again, a great example about how manipulating nutrients available to the trees can manipulate the size of that tree, which obviously is of importance to us. So the design of this experiment is sometimes called the impact study. That stands for Intensive Management Practices Assessment Center. Doesn't really matter. It's a study located up near the Gator Nationals racetrack north of Gainesville, Florida. And you may visit this when you take silviculture. Jason Vogel may take you there. But at any rate, this study had 4 different treatments. It had a control treatment where trees were planted and they do nothing. It had a weed control treatment where all competing vegetation was removed. Okay? And then there's a fertilizer treatment where fertilizer was added. These are all on different plots, so we can measure them separately. And then this is a combination of weed control and fertilizer. And then this graph shows then from age 3 to age 18 the amount of stem biomass, so how big are the stems in those different treatments. So what you can see is that the circles, the control trees, are much smaller than the trees that either had weed control or fertilizer. Okay, so let's think about that a little bit. So at age 18, stem on the control plots was about 45 tons per hectare. 45 tons per hectare of stem on the controls. Whereas on the ones that receive fertilizer or control of competing vegetation, it was about 100 tons per hectare. So more than twice as much. So we grew twice as much wood by either adding fertilizer or by controlling competing vegetation. So this is interesting. You know, note that this is weed control. And this is fertilizer. Okay? So on those fertilizer plots, they received fertilizer, but allowed the weeds, the competing vegetation to grow. Well, that means the competing vegetation was getting plenty of nutrition, but so were the trees, and that increased their productivity. But on the weed control plots, there's no added fertilizer, but by removing the competitors, that freed up soil nutrients to go into the trees. So you can see in this case, freeing up soil nutrients by getting rid of the competitors had almost the same effect as adding fertilizer. When you did both, you got a little bit of extra productivity, but not a lot of extra productivity. So that's an interesting result. It tells us a couple of things. One, it tells us that the main things that those weeds weeds or competing vegetation were competing for was nutrients, because they had about that weed control treatment had about the same effect as a fertilizer treatment. It also means that in some cases you can trade off the effects of fertilizer for the effects of herbicide or weed control. So those two treatments can have similar effects. That's not across the board, and there are caveats that you'll learn about in silviculture, but those two tools, fertilizer addition or herbicide, in some cases can trade off for each other a little bit, especially in terms of controlling nutrition. So that's an important effect. And clearly, this site was nutrient deficient. Now, we don't know what element was deficient because the fertilizer treatment had everything. It had NPK, magnesium, potassium, phosphorus, calcium, boron, iron, and so on. So we just know that one or more elements in that fertilizer was deficient, but we don't know which one. Okay, what is the mechanism of increased growth rate when we add fertilizer? I already touched on this a little bit when we talked about carbon allocation in a previous lecture, but I want to talk about it a little bit more. For a long time, it was thought that addition of fertilizer increased growth rate in pines because it increased photosynthesis rate. So we've seen this graph before, which shows that net photosynthesis rate tends to increase, for instance, as nitrogen concentration increases. So increasing photosynthesis rate by adding nutrients makes more carbon available for growth, and the trees can grow faster. But in pines, it turns out that's probably not the case. So this is a pot study where people measured net photosynthesis rate on the y-axis in trees that receive fertilizer and control. So the open circles are control trees. These are in pots. And the closed circles are fertilized trees. And what we see, so fertilization occurred on day 0, and this is a magnification of those first few days. What we see is that when we fertilize those pine trees, the photosynthesis rate does increase a little bit. And it increases for a little bit, but that after a couple of months, that elevation in photosynthesis rate is done. It's gone. So what we found in pine is that fertilization has an ephemeral effect on photosynthesis rate of individual needles, and that stimulation of individual needle photosynthesis rate is short-lived. So it doesn't explain the increase in productivity that we see in pine forests when we fertilize. What we do see, however, is a shift in allocation. We see a shift in where photosynthate and biomass goes. So this is a summary of data from fertilization studies in a number of pine species. So these are a number of different pines. This is radiata pine. This is Scots pine. This is red pine, ponderosa pine, and you all know this is slash pine. So what they did was look at the ratio of NPP, this is growth, the ratio of growth of foliage to root. So this is a ratio. So when this ratio is larger, that means foliage is growing more than roots. Okay, so what they show is that when we fertilize, that ratio is larger. That means when we fertilized any of these pine trees, they tend to grow more foliage than roots. So pines tend, when they're fertilized, to increase foliage growth and reduce root growth. So really, fertilization doesn't change the effect on photosynthesis rate is not that important. What fertilization does is shift allocation towards foliage, allows the production of many more leaves, and that greater number of leaves fixes in total more carbon. So we can think about that in the context of this bucket model of carbon balance. So, let's say this is before fertilization, and root growth is fairly large here. When we fertilize, that root growth goes down and leaf growth goes up. When leaf growth goes up, that feeds back, and we get a much larger amount of photosynthesis, and therefore much greater input of carbon to the bucket, which enables then increased productivity, increased stem and branch growth. So that's really the mechanism of growth response of pines to fertilization. Now, in some hardwoods or angiosperms, fertilization may cause increased growth due to increased photosynthesis rate of individual leaves, because those angiosperms may have greater plasticity or flexibility in photosynthesis rate, so they can adjust their photosynthesis rate way up. Pines, because they're adapted to nutrient poor conditions, just don't have the ability to increase their photosynthesis rate much. So really what we end up seeing is the shift in allocation. And when you go into a fertilized pine stand and look up, there's just a lot more leaf area, a lot more needles. And that's really the mechanism of fertilizer growth response in pines.